talk about one of his favorite subjects. I guess this is almost as long as you have done research, something like that, right? So Professor Peng received his PhD from University of Pittsburgh in 1975, and then went to Sakal, and also returned to Pittsburgh for postdoctoral research before picking up a position at Los Alamos in 1978. I think he covers both nuclear experiment and particle experiment, and very diverse. I was just asking him what is his focus at the moment. In 1993, he became an APS fellow, and I think before and after that time, our department tried twice to recruit him. In fact, in 95, we did make him an offer, but it didn't work out. In 96, he became a lab fellow at Los Alamos, and in 2002, he moved to his present position at Illinois at Urbana-Champaign. So initially, he told me that he could talk about dark photons, but he didn't feel he was ready. So, but I think he's the world expert to tell us about flavor structure of the nucleon C. So, JC. Jen-Chieh is too hard to pronounce.
Well, yeah, thank you for the introduction. Actually, I was hoping that I can spend my sabbatical quietly in academia Seneca, but somehow George convinced me to come here to give the talk. So as you can see that this probably is not what you expect. It's not having to do with particle physics. On the other hand, I would think that, yeah, well, and also I'm not a theorist, so that's another, another problem. So let me, and some of you might have heard at least part of this talk before. So for those people who have heard part of this talk, I assure you that we have some new results to show. So just be patient. So the title of this talk is Flavor Structure of the Nucleon C. So you might ask that this is sounds like we know everything about the Nucleon C. After all, the Nucleon C was known for very, very long time. If you look at the textbook by Frank Close, I think in the 1980s, for example, he was showing this cartoon for the proton C, as well as the valence quark distribution. So you can see that this distribution were plotted as a function of x, which is just the fraction of the proton's momentum being carried by different type of partons. So you can see that this is a very simple picture. You have the U quark and D quark is roughly a factor 2 more for the U quark than the D quark, and they are peaking at rather large the valence quark region for the U and the D. And for C quark, you can see that it's very simple. The U bar and the D bar and then the S bar, they were all assumed to be the same, okay? Having the same distribution, the same magnitude, and also their presence actually vanish once you go to the valence quark region. So once the X goes above 0.3 or so, there's no longer any C quark contents there. So that's very nice and simple, and so it's assuming basically that C is just at the small X region, and also it's SU3 flavor symmetric. So as you will see from this talk that actually the Nucleon C is actually full of surprises once you take a closer look of the Nucleon C. Okay. So in this talk, I'm going to describe certain recent development on our understanding of the Nucleon C. I will cover this recent attempt to isolate the so-called intrinsic C components, okay, from some Brillouin experiments and from some DIS experiments, deep inlet scattering experiments. And then I will discuss some connection between this intrinsic C and also some lattice kind of picture. In particular, I try to make the connection of this concept of intrinsic and extrinsic C to the concept of connected C and disconnected C, okay, in the lattice. In particular, I'll show you how to separate these two different components. Then I will also show some recent results on the X dependence of this flavor asymmetry, as well as the strange quark over non-strange quark, the X dependence. So actually, this is based on some recent review article. Actually, I worked together with Zhang Wenzhen, who is in academic Sinica. So if you would like to know more details, you can probably find out those details there. So let me start with the first topics, which is the search for the intrinsic quark C. Okay. So it actually has a long story. I think in 1980s, there is a paper by Brodsky, Hoyer, Peterson, and Sakal. So at that time, they actually wrote down something quite simple. They say that if you look at the proton structure, as we know that it consists of the UUD valence quarks. But then if you go to the next Fock states, then it involves 5 quarks. So you have the QQ bar, etc. Okay. Therefore, there should be non-zero probability for the proton to have this kind of Fock states involving 5 quarks. And if you look at the quark structure here, there is an anti-quark there, okay, Q bar here. Therefore, Q bar would be a C quark. Therefore, for this kind of 5 quark Fock states, this actually provides a very natural mechanism for having the C quark here. And if you look at these components, if proton has non-zero probability to have this 5 quark states, then the proton momentum in this case will be shared by these 5 quarks. Therefore, one can conclude just from that this anti-quark here must be carrying a significant fraction of the proton's momentum, roughly 1/5 of the proton momentum. Therefore, in that sense, the momentum distribution of this 5 quark states will have a momentum distribution, in this case, which is more like a valence quark distribution. So this is what they call the intrinsic C. It's really valence-like, and they have very simple and plausible idea, which is that for this so-called intrinsic C, it's different from the QCD-C, which come from the gluon splitting, for example, into a quark-anti-quark pair. Here you can see that the momentum of the gluon is shared by the quark C. Therefore, you can it's very natural to expect that for this QCD type of gluon splitting process, you will get a C distribution which is peaking at very small momentum. So this is the conventional C-like distribution, and this is the what they call the intrinsic C. So this is very interesting because this Q can have any kind of flavor, up, down, strange, as well as charm or beauty, etc. So if you focus on the charm quark configuration, then this actually provides a mechanism for producing a charm quark C, which is valence-like. In other words, it's peaking at rather large X.
So, these are two different representations, obviously, that you mix to make the proton. I mean, this, so you assume mixing between the pentaquark and the 3-quark.
That's right. Yes, so you actually will have different kind of amplitude for the, so suppose you take snapshot of the protons. Sometimes you will just see 3 quarks, and sometimes you will see 5 quarks here. Yeah, I think we reserve the pentaquark to this exotic pentaquark, but you are right that there are 5 quarks here. Even though the explicit flavor can be just represented by 3 quarks. Okay, so this is very interesting because if you have this kind of components, you provide a very natural mechanism for having a Chang quark distribution peaking at relatively large momentum. Therefore, if that's the case, then this Chang quark can contribute to the Chang hadron production at the large x or with a large momentum. So indeed, when they look at the early data, either from the deep inlet scattering involving, in this case, a Chang production, or from the ISR data where the lambda C is produced in the PP collision, if one look at, for example, the large excitement, which means that the forward rapidity region, then the data are not that good. However, in some model-dependent comparison with the data, it looks like the model which contains the intrinsic IC is the intrinsic C can describe the data better at the large momentum region. So that would be the signature, that because this intrinsic Chang can contribute to the production of the Chang particle at the forward momentum, at forward rapidity region. So this looks like some tantalizing evidence. I think this, for some reason, this became a very favorite subject of Brodsky. So he has been carrying this slides in his briefcase for the last 20 years. And so he, in every talk he gave, he would show this, just showing that if you look at the Chang particle production at the forward rapidity region, you can see that there is an enhancement above the theory calculation. So the only way to explain those data would be to add this intrinsic Chang components there. So several years ago, before that, so this was also taken seriously even at Collider, for Collider experiments. For example, at Fermilab, I think these are the D0 data in P-bar-P collision. So what they are measuring here is actually the ratio of the Chang jet plus photon. They compared this quasitron versus the Chang versus the B quark versus photon. Okay. So if you look at this ratio, these are the data. Again, the error bar is rather large. It's plotted as a function of the PT of the gammas. You can see that when you compare the data with the next to leading order calculation, the large momentum data actually are above the theory calculation. If, for example, one add the components of this intrinsic charm, then I think it's in better agreement with the data.
So what is the PTIA version 6.4? It looks pretty good.
Right, that's right. Therefore, it's clear that both the experimental L bar and also the intrinsic uncertainty of the parton distribution actually will make this conclusion not so convincing, actually. Yeah,
how high X are the X, your 10X corresponding to these are how high?
That's right. I don't know for this particular experiments, but if you look at I will show you the model prediction. The model prediction of the intrinsic charm distribution in terms of the X later.
So what is the amplitude for this 5-part configuration?
That's right. They were just using the amplitude which was assumed in the Brodsky's original paper. Yeah.
So what's the magnitude for this?
I think it's on the order of 2% also.
Fraggle independent or Fraggle dependent?
No, for the charm, yes.
For the charm.
For the charm. As you will see, that's really a very optimistic assumption.
And how about the bubble? Because you show this ratio between.
That's right. It was using the charm components assumed in the original paper, which is about 2% also.
So I just have a very naive question. Since you express the proton state
Right.
with the 3 quark and the penta quark or
Right.
something, and do you have this constraint on the mass? Because the proton has mass, right? So the amplitude of this various states should be constrained.
That's right. So that's a very good question. I think later on, when you look at the expression, okay, for the distribution, you see actually the mass of the proton enter, and also what you assume the mass of the quarks. you have to use the constituent quark mass there. It's basically an off-shell effect there. Therefore, actually, how off-shell it is will be reflected by the probability there. So it has to be not so much off-shell in order for that components to be. Anyway, I'm going to address this. Okay, so this was taken somewhat seriously by the Parton distribution people. So they say that why don't we just do a global fit of all the existing data, rather than just cherry pick the right data to make the conclusion that whether the intrinsic charm is there or not. So I think 2007, the CTAC collaboration, they try to fit all the existing data by including or not including the intrinsic charm components. So for example, you can see that if you include the intrinsic charm component, then it's going to affect this region actually greatly. So the conclusion of this study was the following, that if you add 1 or 3% of the intrinsic charm, okay, to the charm distribution, which only affect the distribution at the large X region, it has almost no effect on the chi-square of the global fit. So in other words, the existing data are really not sensitive to the charm quark distribution at the large X. So if you look at the conclusion of this paper, they say that we find that this intrinsic charm is constrained to be either from 0 to about 2 or 3 times larger than the estimates from Brodsky's paper. So based on this, one can already say that there's really no conclusive evidence of this intrinsic charm. So this is still an interesting topic. Even very recently, people continue to do some global fit with more and more data available, and they still reach the conclusion that if you look at the chi-square, with or without the charm, you can see that that as you add the charm components there, the chi-square still has a minimum at the 0 intrinsic charm region. Therefore, based on this kind of global fit, one can actually conclude that intrinsic charm at most carry less than 1% of the proton momentum. There are other studies, other conclusions. I will not go into detail. So several years ago, actually, while I was spending a sabbatical here with Zhang Wenzhen at Academia Sinica, so we asked ourselves a very simple question, which is that if you look at this original paper by Brodsky, this quark here can be any flavor. Therefore, it is possible that one can also have these 5 quark components with the light quark here. This Q here can be UU bar or DD bar or SS bar. From some very simple arguments, you can conclude that the probability of having this lighter quark intrinsic C is actually proportional, inversely proportional to the mass of the quark squared. Therefore, if you go from the charm to the much lighter U, D, or S quark, then the probability should actually go up significantly. So the question then is that why don't we try to look for experimental evidence of this intrinsic quark C, not for the charm quark, but actually for the up, down, or the strange quarks. So that was the very simple motivation at that time. So the first step actually is that in order to search for this intrinsic light quark C, you would like to know what to expect. Therefore, the first thing is that what would be the momentum distribution of those light quark C that you expect. So fortunately, the expression was given by Brodsky et al. By this expression. It's a very simple expression. It just say that we have 5 quarks here. These 5 quarks momentum will have to add up to 1, okay, in terms of x, just telling us the proton's momentum is being shared by these 5 quarks. And then this is just tell how off-shell they are, and that actually these will have a maximal value if all the quarks are moving at the same velocity. Okay. So by using this formula, you can actually calculate what do you expect to be the momentum distribution of this intrinsic C quark here? Depends on the flavor, whether you have a C charm or strange or up and down, you can see that you shift somewhat. Okay. But a common feature is that they are all valence-like. They are all peaking at relatively large x. So this would be what one expects. If you have experimental evidence of the intrinsic C, they should look something like this.
Let's see, with Brodsky's assumption for this P,
Right.
what does it correspond to regarding to the spatial distribution of this?
Right, very good. So you can see that this actually is a distribution describing actually the momentum as a function of the momentum of all these 5 quarks, right? Therefore, in order to go from here to here, you actually have to integrate over the other 4 quark spectators. But you can do that. Once you have these distributions, you can just integrate over x1 up to x4. Then you basically get the momentum distribution of the 5th quark. The 5th quark, you just call that the Q bar there. Okay.
But what does it correspond to, the spatial distribution?
Yeah, that means that suppose you take a snapshot of these 5 quark components, what is the probability that the first quark will have a value of x1, the second quark will have value of x2? They have to add up to 1, right?
I know, but my question is, I wanted to get a better intuition. For example, this QQ bar,
Yes.
are they stick to each other or they are very far apart?
Yeah, in this case, actually, it's the simplest picture. Therefore, there's totally no correlation
No
between that.
correlation.
Yeah, okay.
So
There's
they-
only kinematic effects in the sense that they have different kind of mass. Therefore, you can see that this expression, if you look at this more closely, you can see that this actually maximizes if their velocity are the same. Therefore, if you have a heavier quark there, you can see that the velocity being the same as a lighter quark means that it's actually carrying more momentum. Therefore, the heavy quark actually, this is why the C bar here is peaking at a somewhat larger momentum than the lighter.
I'm more interested in the correlation between QQ bar and the same place.
That's right. In this model, there's no correlation
No
except
correlation.
just this is almost just like a phase space kind of argument. Okay.
Yeah, it's a very simple formula there.
That's right.
There's no interaction.
You can, yes. It's very simple. So this is really, we find this to be a very attractive feature because, you know, if the model is too complicated, you can predict anything you want. But this is very simple, therefore we would like to check that. Okay, so this is what you expect. Okay, suppose you have a lighter intrinsic C. This will be their momentum distribution. However, this is not enough. Just because you know its distribution, you also would like to solve the important challenge, which is how do you separate the much more abundant so-called extrinsic C coming from the gluon splitting, the ordinary QCD-C, from this presumably much smaller components of the intrinsic C. So at that time, we just saw that there might be two ways to extract the intrinsic C. The first that you can probably try to identify some experimental observables which actually have either no contribution or very little contribution from the ordinary extrinsic C. So if you can identify those kind of observables, then that would be ideal for isolating or extracting the intrinsic C. The other is that, as we shown in the slides before, you expect them to have different momentum distribution. Therefore, perhaps you can separate them from the different momentum distribution, which is characterizing the extrinsic from the intrinsic C. Yeah, the reason is that intrinsic C is valence-like and peaking at a larger x, and extrinsic C is peaking at the smaller x. So for the first approach, actually, this happened to be what I have been doing for a long time. So one can readily look at this quantity, for example, the difference of the D bar and U bar. Okay. So if you look at the conventional contribution for this C quarks coming from the gluon splitting, then one expects that this conventional contribution, or the so-called extrinsic C, they must pretty much be equal, okay? Because the quark mass are very similar, and then this process should give equal probability for the D bar and U bar. So if you make the difference of the D bar and U bar, this conventional contribution to the extrinsic C must cancel largely. Therefore, what remains must be coming from the intrinsic C.
But Jen-Chieh,
Yeah.
I'm still puzzled with all these pictures. So you do not regard ions as part of the Nucleon C.
You are not talking about the slides, you're talking about earlier slides?
Because ion, in that case, UU bar or DD bar will be correlated.
Yes. That's right.
And ion can also decay into UU bar or DD bar.
Right.
So how can I reconcile these pictures?
That's right. So
I think
as you will see, we try to group the pion into one type of the intrinsic C. Yeah.
I mean,
You are raising a different issue, which is in this very simple model by Brodsky, there is no correlation built in, okay, for the quark and anti-quark. Therefore, it's ignoring all this hadronic degree freedom, like the meson degree freedom and so on.
I think you're going at higher Q squares.
Sorry?
Aren't we discussing about higher Q squares?
These are also very high Q square.
So
Yes.
there's no pi. I think the pion doesn't make a.
Yes and no. Yes and no. Actually, that's a
I
very
don't
interesting point. That's what one would believe, that the pion actually would not play any role at the high Q square. So as you will see later on, that's totally contrary to what we find experimentally.
Okay. Interesting.
Yeah. So that's actually the next slide. So this actually was a major topics we tried to study at Fermilab since about 20 years ago. So what we measured there actually is the so-called Drell-Yan process. I'm sorry, I don't have a slide to show the Drell-Yan, but you can see that in the Drell-Yan process, you use high energy proton beam. And then you look at the electromagnetic process involving the quark-anti-quark annihilation. Therefore, if you measure the decay of this virtual photon into a lepton pair, then essentially you can probe the anti-quark distribution in the nucleon. So this is a very powerful way, experimental technique, to isolate the C quark, the anti-quark distribution. So if you focus on kinematic region where the second term, for example, is negligible, then the cross-section is just directly proportional to the C quark distribution. So we did that measurement, and we did the measurement on the hydrogen versus deuterium, and it's very simple to show that if you just compare the neutron versus hydrogen cross-section, this ratio is directly related to the anti-quark distribution of the U and the D. Okay. Therefore, if the U and the D C quark have the same distribution, you can see that this ratio should just be equal to 1. But experimentally, we saw a very surprising difference, that they are actually deviating from 1, and based on how much they deviate from 1, you can actually see that the D bar and U bar, the ratio can actually deviate from 1 at some X value. In fact, it's almost a factor 2 more D bar than U bar. So based on these measurements, which actually was very surprising at that time, one can actually obtain the flavor asymmetry. So based on D bar over U bar, you can actually construct this quantity we were interested. So you have the D bar minus U bar,